Welcome to this talk about online extractability in the quantum random oracle model. My name is Jelle. This is joint work with Serge, Fehr, Majenz and Schaffner. Let's first talk about what extraction is and where we find it in cryptography. Suppose we have a protocol where some algorithm A sends messages that depend on a secret S, where in an honest execution S indeed remains secret. But at the same time there exists an extractor algorithm which, given some kind of enhanced access to A, is able to retrieve the secret S. I'll explain about what this enhanced access is a bit more in a moment. Let's first look at some examples where we encounter this situation. Like in zero knowledge proofs of knowledge, such as the Sigma protocol that you see here. This is a 3-round interactive scheme that allows prover Alice to prove her knowledge of a witness W in some MP relation to a verifier Bob. In the first round, she sends a message A, then the verifier replies with a random challenge, and the prover responds with Z. Here, indeed, this message, the response Z, depends on the secret witness W, but the zero knowledge property ensures that the verifier will never be able to learn W, while still we want that the verifier Bob is convinced that Alice knows the witness if she is successful in producing the right kind of response. So how do we show that? Well, by proving the existence of an extractor that, given enhanced access, in this case the power to rewind the prover, so to run it multiple times back and forth. Given this rewinding access, the extractor is able to extract the witness W. Then there's the example of extractable commitments. And perhaps a bit less obvious, we also need extractors in proving CCA security for encryption schemes or key encapsulation mechanisms. CCA security is a strong kind of security where the adversary is supposed to decrypt a challenge ciphertext, but with the help of a decryption oracle that gives him the decryption, the corresponding plaintext to any ciphertext that is not the challenge ciphertext. And well, then in doing the security reduction, we have to simulate this decryption oracle, which means that for any given ciphertext, we have to be somehow able to extract the corresponding plaintext without using the secret key. So that's another example where extractors come in play. Then there's different flavors of extraction. One property for extractability is so-called straightline extraction, which means that the extractor works by doing just a single run of the algorithm he's extracting from, so no rewinding access. And this is indeed often the better, the preferred mode of extraction, because it gives a better loss factor, since the extractor doesn't have to rely on the algorithm succeeding multiple times. And well, obviously it also gives a better runtime for the extractor, since it has to run the algorithm only once. Then we can speak of on-the-fly extraction if it happens during the execution of the algorithm instead of afterwards. And this is indeed the thing that we need for this CCA security proof, since well, we want to do extraction already at the moment that the decryption oracle is queried, and still be able to continue the run of the adversary afterwards. And in particular, this means that the adversary should not be able to detect the extraction, because, well, if it would detect the extraction, then it would maybe just abort and refuse to continue. So if we have an extractor that satisfies both these properties, then we say that the protocol is online extractable. And that's indeed the goal of the current work. Okay, this enhanced access, I've already told you about rewinding, which is indeed used in a reduction for a proof of knowledge, but also in proving the zero knowledge property. Another form of enhanced access, often used in extractable commitments, is that we can give the extractor some trapdoor information. And then finally, there's the random oracle model, where some protocol that uses a concrete hash function, where we model this hash function as a truly random function that the algorithm has to query. That also gives the extractor some extra powers, namely if we allow it to simulate the oracle to the adversary, which means that it can see all the queries that are coming in. And this is used in, for example, hash-based commitments, commit and open protocols, which I'll also touch upon later in this talk, and the CCA security application that we talked about. Now, of course, the question is, can we do something similar in the quantum random oracle model? To answer that question, let's look at an example, namely that of a hash-based commitment in the classical random oracle model. Here we have an algorithm that wants to commit to a secret S, and it does so by concatenating S with a random string R, and then hashing the resulting string X, and then output C, the hash of X, as the commitment. Now in a commitment we want the adversary to, at some later point in time, to open the commitment by simply outputting X, and then we can verify whether this was indeed the thing that was committed to by hashing it again and checking whether it equals C. But now suppose that for some reason we want to already know what's inside the commitment C the moment it gets put on the table. This is again something that in an honest run of a commitment scheme should not be possible, but with the enhanced access of being allowed to simulate the random oracle and interacting with the random oracle queries that the adversary makes, it should be possible. And indeed, in the classical setting, this is pretty straightforward. Namely, when we simulate the oracle using the so-called lazy sampling technique, which just means that we start out with an empty list, also known as a database, and then at every incoming query we check whether the input being queried was already in the list, and if it was not, then we sample a fresh random value y and mark down in our list that the function h maps this input x to this fresh random value y. And now the moment that this C is put on the table, we can just go through this list and try to find some x that indeed maps to C, where of course we know that if the adversary at the end of the run is able to produce an x that maps to C under H, then he must have queried it before outputting C, so we will be able to find it in our list. But if we now turn to the quantum setting, in the quantum random oracle model, there the adversary is allowed to make superposition queries to the oracle, and there's no longer a way to produce a list like this, because there's no single input being queried at every query. And in fact, we we cannot write down anything about the query that the algorithm makes because it's a quantum state which we cannot copy. Fortunately, though, there is a clever way around this, introduced by Mark Henry in 2019, the so-called compressed oracle technique, which is a way to simulate the random oracle H in such a way that every query that the adversary makes creates some entanglement between the internal state of the adversary and that of the oracle. And we again get some kind of database across many registers, one for every possible input X, and we can then interpret no entanglement at the X register as an empty position in our database, and if there is some entanglement between that register labeled by an input X with the adversary, we can interpret that as the adversary having queried this entry X. But of course, the queries are still in superposition, so what we get is actually a quantum state that is a superposition of many different databases. And in general, the internal state of this oracle can be a mixed state. But one thing we do know is that it's supported by basis states that represent a database of such a form that at the ith query, at most, I different entries are non-empty. And this gives us some hope, at least, that we can still retrieve some information about which inputs have been queried or not. But this being a superposition of databases, we would have to do some kind of measurement. And that might be a problem in our goal of constructing an online extractor, because, as I've explained before, in this situation we do not want the extraction to be noticed by the adversary. So in other words, we have to find an extraction measurement on this quantum state in superposition over many databases and prove that this measurement is not detectable by the adversary. That's indeed what we do in our paper. We give the following measurement. I won't go into very much detail, but one thing to note is that it's defined in terms of a relation R. So we're projecting on output values Y in a register, an input register X, if X and Y satisfy some relation. And then, well, for the measurement we use these composite projectors that basically say, is there an X such that the value in the register X, Y satisfies the relation R together with this X. If so, give me the first such X, or maybe such an X does not exist. That's the measurement, and then to prove that it's not detected by the adversary, we bound the norm of the commutator of this measurement and the compressed oracle unitaries, and the unitary that describes the evolution of the simulated oracle. And we bound it in terms of a parameter specific to this relation from the previous slide. The parameter gamma r, it just asks for the highest number of y's that satisfy this relation for any given x. Yeah, so intuitively, knowing that some y satisfies the relation together with x, that should pretty much pin down the value of y for this parameter to be small. And if it's indeed small enough, then the bound of this commutator is negligible in the output size of the oracle. So again, if that's big enough, then the commutator is small, hence we can move this measurement for the purposes of analysis towards the end of the run. And of course, introducing a measurement after the adversary has finished its run does not influence the behavior of the adversary, aka the adversary does not notice the measurement. Putting that in more algorithmic terms, what we show is that there exists a simulator S that has both a random oracle interface and an extraction interface, such that for any algorithm that makes not too many queries to the oracle, we get the following. If at some point the algorithm outputs C after interacting with the random oracle interface in quantum superposition, then we can take this C and input it to the extraction interface, and it will, under the hood, perform this measurement, give us some x prime, and now our main theorem says that we get a promise on this x prime, namely that the x that will later be output at the end of the run of the algorithm, it either equals the x prime that we got from the measurement, or else this x that the algorithm outputs does not hash back to C. So in the current example, that would mean that X is not a valid opening for the commitment C. Yet in other words, we can either extract what's inside the commitment as soon as it's output by the algorithm, or else the algorithm itself does not know how to open this commitment. That's for the simpler example that we've been talking about, but in our paper we have a more general statement that says for any T as an intermediate output, where we just have to promise that this T is equal to a function f applied to x and h of x, with the property that there are not too many y's for this function that map x to this particular value t. So given t and x, y should again be pretty much pinned down, then we get the same promise as in the simple example. And indeed this slightly more general form of the statement is what we need in this CCA security proof, where now the function f is the encryption function, so t is the ciphertext, x the plaintext, and y equal to h of x is the randomness used in the encryption. And then if the adversary puts a ciphertext t on the table, and if t is a valid ciphertext and the scheme is such that a valid ciphertext must be of this form, by which I mean that the randomness used for the encryption is the hash of the plaintext, then this ciphertext must have been produced by first querying x to the random oracle, and we will be able to recover x from the database and use it to simulate the decryption oracle. Now, that's our main result. Let's now look at some applications that we give in our paper. The first is that of a commit and open protocol, which is a particular kind of Sigma protocol, where now the first message consists of a couple of hash-spaced commitments that we can, where we can again model this hash as a random oracle and use our technique to extract the messages inside this commitment, which taken together allow the extractor to reconstruct the witness W. Hence we can show tight online extractability of generic commit and open protocols. We don't need any of the additional properties, collapsingness or unique responses, which is required for previous techniques that use rewinding. And furthermore, these previous techniques incur a cubic loss on the success probability of the adversary. So if the adversary succeeds with probability epsilon, the extractor succeeds with probability only epsilon cube. Whereas we have a tight reduction and do not lose anything at all. This CNO protocols are used in the popular MPC in the head paradigm, which is a way to use multi-party computation to create interactive proof systems. And this is in fact what underlies the post-quantum signature scheme PICNIC. So we get a better security reduction for PICNIC, but I have to add to that PICNIC is a signature scheme, so it's not interactive, it's non-interactive, and it uses the Fiat-Shamir transform to remove the interaction. And the analysis of the current work is not sufficient to give a completely tight reduction for the non-interactive variant, but we actually have a follow-up work where we do achieve also a tight reduction for the non-interactive version and hence for the PICNIC signature scheme. And this follow-up work is presented in the poster session at this year's Qcrypt, so find us there. Then the other application, I already briefly discussed it. It's the Fujisaki-Okamoto transform. This is a transform to upgrade an encryption scheme to this strong CCA security notion. We use our technique, as I explained 2 slides ago, to give a complete security proof for what we call the textbook FO transform. That is the original transform without any additional features that were added to facilitate a QROM proof. Previous works required such things as deriving the session key as H of MC instead of just H of M. Deriving it just as HM makes the scheme more efficient. There's also no need for a key confirmation hash, which increases the size of the ciphertext that has to be sent. And our reduction works for explicit rejection as well as implicit rejection variant of the Fujisaki-Okamoto transform. And this transform is actually used in the key encapsulation mechanisms that have recently been selected by NIST as the new post-quantum schemes. So summarizing, we were able to lift a powerful extraction method from the classical random oracle to the quantum random oracle model, and it works straight line and on the fly and online. We use it to give the first tight reduction of commit and open protocols and the first post-quantum analysis of the textbook Fujisaki-Okamoto transform. Those are the applications that we give in our paper, but in general, any application where the adversary outputs some T and promises to later output an X that satisfies our pinning down requirement, we get an online extractor for that. Thank you for your attention. Please come to the live session on Thursday, September 1st. Then I can answer any questions.